Today we're going to talk about coding for the project, and also we're going to look at after we're done with that, we'll look at what people are currently doing, and then stick around and we'll do some working on things together and making it work. As far as coding goes, give me some slides, Corey.
Oh yeah, slides. Click.
More click. All right, so this is summary of what we're doing. Let's just keep going.
Yep.
A real slide with real content. Here we go.
go.
All right, this is much better. This is too much text. All right. So I want to go back for a second and sort of refresh and go a little bit deeper on some of the basic concepts of how this stuff comes together, so that we can then understand what we're talking about when we start talking about code. When you have a part in your project that you can put some code on that that controls how your project is going to behave, that part is called a microcontroller, also sometimes known as MCU, which stands for microcontroller unit, also sometimes written as a micro C for microcontroller. And its purpose in life is that it can somehow interface with the world, or it can in some way receive inputs from the world and then in some way control the world. It has some input, it has some output. And so I think we had one project number 4, which doesn't have a microcontroller. All the 3s and the 5s have them. So if you have if you're working on a useless box, your microcontroller is the rectangular board with like 30 pins on it. And if you are desktop project, or microcontroller is a circular board where like there are some paths on there. And those inputs and those outputs all in some way get connected to these pins on the microcontroller. So that's where all the inputs and outputs go, and we'll talk in more detail about sort of what happens within those. And then all these different things that you connect to your microcontroller, so these different inputs and outputs, they're called peripherals as a general concept. So something like an LED is a peripheral, a motor is a peripheral, like a humidity sensor would be a peripheral. If you have, if your microcontroller has a way to send radio signals of some kind, like that radio thing would usually be a peripheral as well. And those peripherals sometimes have weird names. The 4 that I'm going to call out are shields, feather wings, hats, and bonnets. All of these specifically refer to a shape of a peripheral that is compatible with a specific type of microcontroller. So if you have a microcontroller that is called a feather, which is a brand name from Adafruit, then peripherals that are specifically designed for it are called feather wings. And then some other microcontrollers, peripherals specifically designed for them are called shields, etc. So if you see one of those words, that's what that means. And then another type of peripheral is something called a breakout. That is a thing that is designed so that you can plug it directly into a breadboard. So on that picture over there, this whole thing is a peripheral, and it has like this, little display on it. But it is set up such that on one side of it, it has a row of pins, and those pins you can just stick into a breadboard, and that's what makes it a breakout.
So is this one up here, but you can't see.
You can't see that one. Then your microcontroller is something where you can put some code on it, and so the code that you put on it are basically some instructions for what it's going to do. And a language is a set of conventions for how you make those instructions. There are a few different languages that are common, and we're going to talk about that later. If you're when you're writing this code, basically the way that it ends up happening is that you will write some stuff that is yours, and then you will use some stuff that comes from other people. So the stuff that you write that is yours is very frequently called a sketch, for no particular good reason. And if you see somebody talking about example code, what that means literally that somebody else wrote some example that you're going to copy and paste into your sketch, and then you're going to use it as a starting point. Whereas a library is also something that somebody else wrote, but you're not going to copy and paste it. Library is something that you in some way install, and then it becomes available for you to use. So if you see these words, sketch and example code and library, all of them refer to different kinds of code, but more specifically, sketch is the thing that you're going to do. Example code is something that somebody else did, and you're going to copy and paste it. And library is something that somebody else did, and you can use it, but you're not going to copy and paste the whole thing into your project. And all of that is done inside an app that is usually called an integrated development environment or an IDE. So if you are in an app and in that app you're writing some code, whether it's text-based code or like graphically based code, you're doing that inside an IDE. So
we're going to look at all these things.
We're going to look at all of these things. These are just terms that we're going to use for the rest of our time here.
Yep.
And so with that, give me 2 slides for it, I think.
Yep.
Yes. So I want to talk about what this word Arduino is, because it's a confusing word. So Arduino is a company that was started in 2005 in Italy, and their big thing was that they made hobbyist-friendly microcontrollers, and one of the things that made them hobbyist-friendly was that they included with these microcontrollers an app that you could use to write code. So it was an easy way to get into making hobby electronics. Then they also made some microcontrollers that you could buy from them, which they also called Arduinos. And there, at this point, dozens of these different ones. So you can go to a company called Arduino, you can buy items from them that are called Arduinos.
Here's the team. It was 4 Italians and a Spaniard. Spaniard's the one on the scarf.
Yep.
And it was meant for art students to learn electronics in a weekend.
Yes.
Yep. Okay.
Then other people got in on this. When this became very popular, and it turned out people who really enjoyed it started getting into electronics. Other companies got into it. They started making other microcontrollers, which they also sometimes called Arduinos, but technically they're Arduino compatible, but everybody just called them Arduinos. And when Arduino made Arduinos, they put out this app, which is basically their development environment, which they call the Arduino IDE, which everybody also calls Arduino. And the language that you use inside this app is it's based on C++, which doesn't matter what that really is. But the point is that they also call that language Arduino language. So the word Arduino can mean all sorts of different things. So it would be, in fact, possible for you to write Arduino code in the Arduino IDE for an Arduino microcontroller that you bought from Arduino, the company.
It's too many. That's a lot.
Way too many.
Yeah.
Yes. It's usually obvious from the context whether somebody's talking about the company or the piece of hardware or the app that they're working in, but it can get confusing. And because other companies got in on this and they have their own brands, you could also be writing, for example, Python-based code in Microsoft MakeHaven IDE for a Metro Mini microcontroller, which is something that that you bought from Adafruit, because that's one of the companies that makes Arduino compatible things. If you see the word Arduino, it could mean a lot of different things, but it's usually going to be clear from the context whether somebody's talking about an item that you can hold in your hand, in which case they're talking about a microcontroller, or whether they're talking usually about the company as sort of like the most common how to use of it.
2 big simplifications
yes.
for this. One, you remember the chip shortage? It was based on the complexity of this supply chain, like how nuts all those different things are. And the second one, and this is a rule of thumb, not a rule. If you Google Arduino on Amazon, never steers you wrong. You're going to buy the right thing. It'll work with the IDE. It's great.
Yeah.
98 times out of 100.
Yeah. Because that's a good point, is that because of the fact that Arduino, the company, made the whole thing, it means that anybody that says that they are Arduino compatible, we're usually making things that work with any of this other thing.
Can you explain IDE again?
Yeah. Here, let me show you. It's this.
So, okay, so that's the code is written in that platform.
This is the IDE
program that's there.
Right.
Okay.
That's the IDE.
So there's a Python IDE, right?
Yeah.
Does every coding language have its own IDE?
Some IDEs that work with multiple different languages, but in short, an IDE is an app that you can go and write code in.
Okay.
So because you can go into Tinkercad and write code, by some measure, Tinkercad is an IDE.
I'm just pulling up other IDEs. Yeah, so this is VS Code is another IDE. There's a Python IDE. The
Would Replit be considered? an
Replit
IDE?
is an IDE.
Yeah.
Mhm.
Can I make an analogy like Google Docs versus Microsoft Word?
Yeah, so
This is like the browser for your.
an IDE is like a word processor. So in the same way that Microsoft Word is a word processor, and Google Docs is a word processor, all of these things are IDEs. What it basically is a word processor that is in some way specifically intended for writing code, which means that it's gonna use different fonts. It's gonna have like easier way to like look up documentation, like so it will have tools for writing code, as opposed to like tools for publishing documents.
Yeah.
And like Word is not a web-based word processor,
Yeah.
but Google Docs is. There are some IDEs that are web-based, like Replit is a web-based IDE.
And we're gonna talk about one of
Collaborate
those.
together.
Yeah. And Python's IDE is just like, yeah, got it down.
Okay.
But it's really like, this is just Notepad over here on the right. It's really just a place for text to go. The benefit you get from an IDE is that it does syntactic coloring, it does other nice things for you. There's some buttons here to upload it, versus this is just like Windows Notepad and just keeps the text.
It's amazing how useful Windows Notepad actually.
Oh, it sure is.
Like a lot of random things. Okay, sorry, next question.
Yes.
Raspberry Pi used to be the big deal, right?
Raspberry Pi is still a big deal. Raspberry Pi is a thing that is called a single board computer, or an SBC. And what that is something that is more powerful than a microcontroller in ways that are a bit of a tangent, and I'm going to skip over it right now. But also means that it is more power hungry than a microcontroller. So you wouldn't want to take a project like the one that we want to build into like a textile Raspberry Pi in it, because you have to have a battery that's like 5 times bigger than if you use a microcontroller.
Okay, gotcha.
But if you want to watch a YouTube video on it, you probably want the Raspberry Pi.
Yes.
You're never ever going to do that on an Arduino.
Okay. Done.
Great. All right. So let's get to something that's more fun than five ways to do Arduino.
Inputs and outputs.
Yeah. So we're going to talk about inputs and outputs for a minute. Everything in the real world is what's called analog, which means that if it's a value that you can read, it can take it can be anywhere in a range of values. So for example, temperature is an analog value. Temperature of the air could be 37 or 37.5 or 38.15 degrees, etc. And analog outputs are things like let's say the speed of the motor. Like you can drive your car at like 60 or 75.1 or 76.17 miles per hour. So the fact that you have this like range and the value could be anywhere in that range is what makes it analog. Analog is hard for computers to do it. Computers are based on a different concept of things called digital. And that concept starts with representing everything as a series of zeros and ones. When you have something like a microcontroller, which is digital in nature, interfacing with the real world, which is analog in nature, then every input and every output has to be in some way interconverted between these different things. So we'll talk a little bit later about how some of that conversion happens. But here what you see is a signal that is analog in nature, and then across the top you see ones and zeros, which is basically a digital version of the same signal, in which all of these sort of messiness of these squiggles has been removed. And in doing so, you lose some fidelity, but also you make it easier to work with that kind of a signal. Alan Turing's big idea back in 20th century was that a digital computer can basically do everything that you would ever need to do with analog signals, so that constraining our computers to working in a digital way does not actually reduce our ability to process analog signals. Yeah. Pulse width modulation, which we'll talk about a little bit more later, is a specific way of converting digital signals into analog signals. Yeah. Or you look like
I do. This is another one that I like to try and summarize. There's a lot of chaos and signals can have noise. Most of us probably remember having bunny ears on a TV at some point, and like if the weather was wrong or you're standing in the wrong part of the room, it would get staticky. Switching over to digital really reduces that, because it takes the noise. You can see how wavy it is in the 1 and 0 zone. it's basically simplifying all that data and saying, if you're high enough, your count is a 1. If you're low enough, you count as a 0. And so it really does a good job of just removing that noise by saying, this is high enough, I'm going to count it as a 1, low enough, count it as a 0, problem solved.
You might at some point have to stop using bunny ears as an analogy.
Eventually.
Yeah. I got another decade.
Yeah, we gotta come up with a. But
Is there, you know who Alan Turing is?
I don't.
What's that? There's a Turing.
Turing test.
Yeah, what's that?
It's a different thing. Alan Turing's a fascinating. You should Google Alan Turing.
Yeah, honestly, he's brilliant. Yeah.
Saved the world and then was forced to off himself because he was gay.
Yeah.
Yeah. Excellent summary.
Yeah.
You could, yeah.
A famous British early 20th century mathematician and computer scientist.
Single-handedly helped us beat the Nazis.
Yep.
Oh, right.
Mhm.
Because of,
He was Benedict Cumberbatch.
yes.
What was that movie called?
Enigma probably.
Yeah, something like that.
Yeah. So yeah.
Anyways.
Yeah. But just
Great.
such a cool character that I
Great story.
in history, obviously, he's a real person.
Yeah.
Yeah.
Okay. If you have a microcontroller, it's going to have a bunch of inputs and outputs, and for you to be able to use it, at some point you'll need to understand what they are and how they work. So first of all, I'm going to give you a general overview of the kinds of things that you might encounter. And then we'll go and look at that picture on the right. That is a picture of a microcontroller that is in all of our useless boxes. So when we're talking about input and outputs on microcontroller, all of the pins on the microcontroller that are input or output pins are what's called general purpose input and output. And that basically means that you can do whatever you want. GPIO is the abbreviation for that. And the most common kinds of GPIO things that you will see on a microcontroller are things that are called digital pins, which actually just means that they're digital only, which is to say that they can't receive an analog signal and do anything useful with it. And they can't output a useful analog signal. So you're going to use those for things where maybe you have a switch, and that switch can be on and off. It would be like a good thing to read with a digital pin. You have things that are called analog pins, which really means analog input pins. And an analog input pin, you can connect something that is analog in the real world, and that pin will read back to you not just a 0 or 1, but a number, but it will maybe break it down into a range from like 0 to 1,000, or from like 0 to 4,000. So for example, if you have a temperature sensor, an analog temperature sensor, and you hook it up to an analog pin on a microcontroller, what you get back is a number that is between, let's say, 0 and 1,000. And there will be some documentation about how that number between 0 and 1,000 is converted to a temperature. But you will get back a reading that's not just 0 or 1, you'll get back a reading that actually represents that analog value. Yes. No.
Vibrating on the wall.
Yeah. And then the third kind of thing that you might see is something called the pulse width modulation pin, which is, as I mentioned earlier, a way of converting digital signals into analog signals. And what that does for you is it lets you create an analog output. So for example, if you were driving an LED as an output, and you wanted to be able to change its brightness. So brightness would be something that is an analog value, because it's not just 0 or 1. You would want to connect that LED to a PWM pin, because then you can say, I want to output, let's say, 50%. Like I want my output to be halfway between 0 and 1. And a PWM pin can do that for you, and a digital pin cannot do that for you. A digital pin could only output a 0 or a 1. And beyond that, there are some things that are not general purpose, that are special purpose IO. And what that means is that you have some pins that are set up to work in a specific way, and the only thing that they can work with is a device that is set up to work in a way that matches that. So these have a variety of different names. There's a thing called UART, and a thing called I2C, and a thing called SPI, and blah, 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 blah. The important thing to know about it is that if you have a device, a peripheral that works with one of these, so for example, you go on Adafruit, you search for a temperature sensor, and it comes back and it says, this product is an I2C temperature sensor. that means that when you hook it up to your microcontroller, you have to hook it up to whatever the I2C pins are on your microcontroller. You can't hook it up to any random pin on your microcontroller.
Yep.
And the way that you're going to find all of these things is that you're going to go on the internet and you're going to say, I have microcontroller called, let's say, Metro Mini, and you're going to say, pinout diagram. And it's going to come back with a picture like this. This particular way of laying out pinout diagrams for microcontrollers is very common, and most of them will have one that's like color coded the exact same way.
Yep.
And it's going to have a list of every single pin, and it's going to have a legend for what the colors mean. So, for example, yellow pins here, which is basically everything on the right side and half of the things on the left side, they're a GPIO. So what that tells me is that they're one of these kinds of pins. And then ADC, which is the same thing as analog, is these 6 pins over here. So if I want an analog input, I have to hook up that analog input to an analog pin, aka ADC pin on this microcontroller. On the other hand, if I want a digital output, I can use any GPIO pin for that digital output. So any one of these would work. SDA and SCL, which are labeled under other, are a particular type of special purpose IO. Specifically, it's I2C. So if I have an I2C device, then it's going to have an SDA pin on it and an SCL pin on it, and I will have to connect those to the matching SDA pin and SCL pin on my microcontroller, which is advanced, and I'm not expecting you to like remember any of this now. The important pieces are that look for pinout diagram. It's going to look something like this. And know that depending on what you're trying to do with your peripherals, you might need to connect it to a specific type of pin. And if you're reading a good tutorial, that good tutorial is going to tell you, you have to connect this to an analog pin, or you have to connect this to I2C. And when it does that, it means that you need to go figure out which of the pins is going to work for that kind of thing.
I'm gonna be honest.
Yeah.
This is way confusing.
It's a lot. It's a lot.
It's a lot.
You want to.
When we do our tutorial, will it tell me exactly what to do? And do I have to?
Usually
For this project.
right. For this project, it will tell you exactly what you need.
Perfect.
Yes. If you go to like a random tutorial on the internet, if it's a good one, it will tell you connect your thing to this pin. It won't tell you connect it to this kind of pin you figure it out. It will say like connect this to pin number 3.
Okay.
Okay. But if the moment that you stray beyond the garden path of following exactly what the tutorial says, like for example, you have a tutorial that like has like 3 LEDs attached to it and you want to attach a 4th one, right? You're gonna need to know where that new LED that you want to add needs to connect. And finding your way through the forest of options is going to be easier if you understand just the general concept of not all pins are made the same. That's the only thing that I really want you to remember.
I will color by number.
Yes.
Yeah, do that. If you do just make the first steps off the path, and you may do that with an Arduino Uno, it has labeled, these are the PWM pins, the little tilde mark, and it says over here, these are the analog in. These are all digital. The silk screen can often be very helpful. The boards are often marked in order to help you do that.
This is one of the advantages of like a bigger board, like the one that Corey just showed, compared to the tiny board that you have. There is no room for such detailed labels on the tiny boards. So for those, usually you have to go to whatever instructions came with the board.
Yep.
Thank you guys for.
Yeah. What's up?
So I see like 14 pins on each side of the microcontroller.
Yes.
Yet I see like what look like, I don't know, 40 pins in that key, the color.
Oh yeah.
So
how's that happen?
So what's happening here is that some pins are first of all, some pins are multi-purpose, and second, some pins have multiple names. So this pin down here, which is called pin 19, is also called A5. And what that means is that if I'm using this as an analog pin, whatever thing needs to know about it, it's going to be asking like, what's the analog pin that you're using? And I'm going to tell it something like A0 or A3 or A5. If I'm using this as a digital pin, then the number that I'm going to use for it is going to be between 14 and 19. So depending on what you're using the pin for, it has a different name.
Okay,
but it ends up being the same like physical pin on the board.
Yeah,
I thought digital pins and analog pins were different.
Yes.
okay. In a Venn diagram of all pins, digital pins are all of them. Those are the same overlapping circles. Analog pins are a smaller circle inside. So all analog pins are also digital pins, but not the other way around.
That's almost always true, but
Okay,
yes.
let's just say it's true.
Okay.
This is about always true. And then there's like an even smaller set that turn into like having this weird SDA, SCL, other stuff. So like most every pin will do digital stuff. And then some of them have even more powers.
So all digital pins are analog pins?
No, almost all pins are digital pins.
Okay.
And then some of those can also do analog. Has to do with a physical thing they need to put into the chip to make it happen. So only some of them get this special upgrade.
Okay.
It's weird. It takes a while.
Yeah.
Don't try and figure it all out at once.
But you're right. The way that I wrote this text on the left is confusing once you try to match it up to the picture on the right.
Okay.
So what should be happening here is that this shouldn't say digital only pins, it should say digital capable pins. Because it is, yeah. Anyway,
Okay.
we're moving.
Yeah. What's up, Puma?
Yeah,
That's true, slides on Fabrication's channel.
I will make sure they're there right now. Yeah, I sure will.
Is it safe to just just go on the idea that like, I don't have any intentions currently of like really getting into electronics, so it's okay that this will just be confusing?
yes.
Yeah.
This, 100%. What I
Okay.
want you to do with this is remember, like 6 months from now, when you try doing your first project that wasn't like set up step by step by somebody else. That there was a slide somewhere that explained some of these concepts, and you can like look up the links to the slides in our Slack.
Just have like a vague
Yeah.
memory of like,
Yeah.
sometimes the pins matter.
Yes, like
Okay.
that is literally the only thing that I want you to get out of this is that some of these words happen and you can go back.
Okay.
Are you done with the?
I'm done. Got it.
Great, all right.
Right.
So we talked about input and output, and that was confusing, but I could try to fit it in 5 minutes. Peripherals are confusing and I will not.
Yeah.
So there are so many different things that you can potentially hook up to a microcontroller. I'm not even gonna bother trying enumerating all the options. I got some pictures here. There's like an LCD display. There's some shiny colored thing.
Pixel rings.
This
That's
over
okay.
here is a capacitive, this is a touch sensor, this here is literally a radio that you can program to communicate with other radios in its vicinity. There's so much stuff you can do.
In a past life, I made 2 different slide decks, each that started with 25 box grid to try and cover the bare skinning the surface of 50 actual items. Categories of items that are involved here. Like it's a nonsense deep well
Yeah.
of stuff that you can attach.
Yeah, it is beautiful and you will get lost.
Yeah.
So the main thing that I want you to remember, again, this goes back to like, 6 months from now, when you're actually trying to do something with this, is that if you buy these parts from a good supplier, it will come with a tutorial. That tutorial will include example code that you can copy and paste into wherever you're doing your thing as a starting point. And it will often come with a library of code that you don't even need to copy and paste. You can just say, I'm going to use this and use it and be done with it. And so to avoid getting lost, rather than just going off on the internet and looking up, I want to buy, let's say, an LCD display, look up an LCD display tutorial and then follow the tutorial and get the part that is mentioned in the tutorial, so you have instructions together with the actual thing to go by.
Without just trying to sell Adafruit.
It's so hard not to.
I know.
To sell Adafruit.
Yeah, it's Adafruit, has Adafruit Learn, Explore and Learn. They have a ton of guides. This is great. SparkFun used to be equally prolific. They're a little less so now.
I still want to have assignments.
But these are, if you go to, they have a Learn page as well.
Yeah.
And so there's,
And I think I mentioned a couple of weeks ago that Adafruit focuses, if you want like if you want textile, anything wearable, anything you'll find on Adafruit. If you want motion control and robots, you'll find more of that on SparkFun. But for like the other basics, they're pretty much comparably good.
Yeah.
Yeah.
Great, okay.
Okay, great. So, with that, let's talk about different ways to get code into a microcontroller. Let's yeah, give them.
Cool. All right, block coding on Tinkercad.
Okay, so all of these different ways of getting code into a microcontroller start in one or two different places. Either you have some kind of visual block type of situation that you're dragging around to make a thing, or you have some kind of like a bunch of text in here, and then that text gets turned into something that the microcontroller can understand. The main difference here being that the block-based thing is way more accessible for beginners, but there is sort of a capability ceiling that you hit at some point where you have to go past the block-based imports and text-based imports if your stuff gets a little more complicated. For Arduino-based microcontrollers, like any one of the ones that we're using in our projects, Tinkercad is one of the ways that you can do block-based programming in your web browser. So you can go into Tinkercad and you drag a microcontroller into the left side where you have your parts, and then you click code on the right, and it looks like this. Thank you.
Yeah, no problem.
And so this is a microcontroller, and then here's a bunch of things that you could make your code do, and you can just drag them over to the right. And then what ends up happening here is that this text-based version of this, which you see on the right, is actually the only thing that we can directly get into a microcontroller. So even if you're starting off with a visual block-based thing, what happens somewhere along the way is that somebody converts it to a text-based representation. So if you're starting in Tinkercad, at the end of your journey in Tinkercad is some text that we need to get into the microcontroller somehow. Can I see the?
So
Yeah.
Yes.
I could, so like, I, as a human who has never even considered that code existed, could like do it in the, could
Yes.
build like the basics of what I want this to do, and then then take it out into text and con one of you into helping me specialize.
Or next time.
Yeah, oh, yeah, yeah,
Backwards one slide or something.
sure.
This bear,
Yeah, he's great.
Yeah,
can you in Tinkercad make this bear do really cool things? Because I think that's amazing.
that's a great question. Scratch is a fantastic option for that.
Scratch.
Scratch and Tinkercad and Pictoblocks, which is what this particular GIF is of, they all use very much almost exactly the same block system.
Awesome.
And I believe that architecture, like the actual shape of them, probably set up by MIT at some point.
I think that
I think it comes out of Scratch.
Yeah.
But it, like you can see how there's a visual similarity between what that GIF is doing and the bear versus what's going on the left of that Tinkercad. They're really similar. The reason why I would use it in a school is that a kid doesn't, their punctuation is terrible normally. God help us when they try to code. So this is a way that you can avoid all of that completely and just get to the heart of like, do you need to do this in a loop? Do you need to do this 3 times and then something else changes? Are there any if-then statements? Like block coding is really, really good for doing that and for really common problems.
Yeah.
It's not just for kids. I used to be good buddies with a guy who became an engineer for Facebook before he worked for Progressive, and to run and design HVAC systems, they use block code for that because it's a very like well-described problem.
Yeah, I would already not, but as an accessibility thing.
Yeah.
Like,
I just like the bear, and I'll never
yes.
any personal issue for my student. So
Okay.
I'll just leave that there.
Yes, you can in fact make some bears dance with
They would love
block programming and
Scratch is great.
it's quite great. I'll get a little bit more into some other kid
Yeah.
interesting things in a second. Yeah.
Our 7th graders, or no, our 6th graders in our computer science class, they use Scratch to actually create an animation, to create like a little scene or like a story. There has to be like a little mini narrative, and they animate it. And then what we do with 7th and 8th graders, which was super fun, is there's a block-based coding program called MakeHaven.
Yes, we're getting to that.
Yeah, yeah.
Let's arcade. You can like program video games with the block.
Yep.
Which is super fun.
We'll keep
Okay,
going.
so I love that everybody knows more about this than I do. This is great. So
Not ever.
Something like this.
so once you if you're in Tinkercad doing your block-based coding and you tell Tinkercad, I want to see what text looks like for that code, or if you're starting with text-based code, eventually you end up in a place where that text needs to somehow get pushed into a thing that goes into the microcontroller. And there are two ways of doing that. And one, I love that. And one of them is to use to download an app that is in a development environment. And the most common one that people use is the one that's called Arduino, which Corey is this is a live Arduino.
Yeah, this is a live Arduino just plastered right on top of it. Yeah.
Yeah. So that's what that looks like. So if I was in here and I had written this code, I could push the upload button as the right arrow here. I choose which microcontroller I have connected to my computer, and I push the upload button. And if my code doesn't have any errors in it, it gets sent to the microcontroller, and then the microcontroller starts doing that thing. So if the code says blink an LED and there's an LED connected to the microcontroller, the LED will start blinking. This here is an older version of the Arduino app. So over there is version 2, over here is version 1. You almost certainly do not care, but there are some modern laptops and modern computers in general will be able to run version 2. But if you have a computer where version 2 is not working for some reason, try version 1, it will probably work. That's the only thing you need to know about it.
Yeah, and like I just pulled up an example of running a servo, which is another type of motor that we could have played with. And then this is example code that somebody else has written completely. It uses, if I hit Control Plus enough times that it's readable, this is like running a servo is actually kind of complicated if you were to write all of that code, but luckily you don't have to. That is including code that somebody else wrote and you don't need to copy paste. That's the library.
Perfect segue, yes. Yeah. So one of the things that is very useful about all of these development environments is that they usually come with a huge amount of example code for all kinds of things you might want to do. Can you show me around the example?
File examples basics blink is one that I bark at teenagers all the time.
Yeah, it just blinks an LED. But there's like literally hundreds of examples built into these things. And usually if you know the kind of thing that you want to do, like are you running a motor, or are you like trying to like do temperature sensing? If you just spend like 5 minutes looking at one of these in the menus in one of these apps, you'll find an example that's in the ballpark of what you're looking for, and it can be a useful starting point. There are examples, like shareable examples that exist within Tinkercad. You can find examples of somebody else wrote. I haven't found them to be as easy to access as examples inside the Arduino app, which is kind of unfortunate because it means that in order to get a really like good starting point, you often have to like jettison the convenience of being inside a block-based environment, and I wish that was not the case. Can you take me to like give me like a NeoPixel, like basic NeoPixel example? Like
yeah, it's gonna take a second, but I sure can.
Well, while Corey's doing that, so if I was gonna start my coding part with the Tinkercad blocks, does it have a built-in like here, learn how this works?
Yes.
Okay.
Do you have
I don't think I have it installed.
Oh,
sadly.
Show me what you have an example of.
So if I go to File, Examples, and then here's a bunch of different options. Like here's for one of those liquid crystal displays.
Yeah, great. Let's do that one. Show me.
Here's Hello World. So this is just going to on that display, and this is that display that was the very first example of a breakout board.
Yes.
All of this, everything that's sort of a dark gray that you can barely read, those are comments. And then here's a bunch of like, these are all the pins that you should plug it into. And there's probably going to be instructions for that written up here for, this is like literally what pins to connect it to. And then down here is, it's going to say, print out on the LCD, the words, hello world.
So the reason I wanted to look at this real quick is that you can see here that when you created a new sketch using an example from that menu, what you ended up with is a bunch of example code that literally got copy and pasted into your stuff. But then in that, there's this line that says include liquid crystal. And that is referencing a library. So behind this line of code, there is a bunch more code that you don't even get to see that is doing things having to do with liquid crystal display. So this is an example of example code that references a library where the example code got copy and pasted into this, but the library is just mentioned and it exists somewhere else, and you don't get to look inside and you don't get to modify the inside.
And you kind of don't want to.
Yeah.
And so that. But the actual code is in there, so when you export that, you don't
Yes.
have to somehow still be connected to the
Correct.
library or
Correct.
whatever.
Right.
This is
Correct.
just like shorthand for our human eyes.
Yeah,
Okay.
exactly.
Yes, it is like C page 15 sort of a thing, but the whole book is in fact there.
Okay.
And if you were in a hypothetical world, someone who already knew how to code but not microcontroller, it would make total sense that we're just like importing a module and then instantiating an object and then using the methods tied to that object. But those words, unless you already code, don't make sense. Great.
Okay, moving on. Oh, right, yeah, so this whole thing that we just did,
Blink, this is one of the examples. Blink is the common example. File examples basics Blink. It lets you see how to use a pin as an output, that you can write them high and low. It's kind of interesting. High means on, low means off. That's all.
and if you have the if you're working on the wearable dice project, the code that is in there is based on this because it's basically doing the same thing, except it's doing it to multiple LEDs at the same time.
Here's a button where you're using a pin, the button pin as an input. So instead of being just an out, it's reading the state of a pin, which is a little different for interesting reasons. But you can read the state of that pin and then take action based on, is the button pressed, yes or no?
And if you are using, again, any one of our projects has some kind of button thing in there that's happening. So
it's true.
Parts of this were the basis for the code that's in all of the projects. All right. If you don't actually want to, or for some reason can't install a whole separate app to like do all of this text-based programming, maybe you started over in Tinkercad and the Tinkercad produce a bunch of text for you, and the only thing that you care about at this point is getting that onto a microcontroller. An easy way of doing that is to go to this website, and you have to do it in Chrome. And then it can talk to a microcontroller that is hooked up to your computer. So you don't have to install a separate thing. It just lets you take text out of Tinkercad and push it to your microcontroller and be done with it.
It's a weird niche package. I don't want to say that it's all use for everybody, but anybody who's stuck with a Chromebook only, it's great. Yeah. And you can use libraries, you can use lots of these things. There's some quirks to it, but it works like a charm.
Yeah.
So there it is.
Most of the tutorials that you will find online, if they're using block-based programming, they'll be in some reference to something like Tinkercad. If they're using text-based programming, they're going to show you how to do it inside the Arduino app.
It's also worth saying this was written by one human, like one individual human. Okay, moving on. Like I said, programming languages are a convention for how we give instructions to computers. There's a different programming language, a different convention for doing that. That's called Python, because it was a Monty Python joke, if I remember. I think that's right. Yeah.
100%.
Can you tell me more? I'd like to ask.
No, sorry. Later.
But within that subspecies of Python-based microcontroller programming, all of these same concepts repeat itself. So Microsoft has a thing called MakeCode, and MakeCode is a block version of this Python-based environment. So you can go into MakeCode and you can move blocks around and you can output Python, and that Python can get on your microcontroller, and then it's the same general plot outline as it was with Arduino.
Yeah, different colors.
Yes,
that's about it.
I like
MakeCode.
Yeah,
sells these little primitive,
yes,
little Game Boy looking devices.
Yeah, MakeCode can do a lot more things besides programming microcontrollers, and it is very specifically pitched at education. So if you're doing any kind of teaching kids how to do programming things, MakeCode is a good place to go. They have a whole subgenre of Minecraft related stuff in there that kids can get really into, and like programming Minecraft to do that I don't know anything about.
I don't
it
want to
exists.
touch it with a 10-foot pole,
Yeah.
but it is good for education things.
Yeah. One thing that I want to mention before we jump to this, go back to the previous slide, is that not every microcontroller is able to do Python things. And so if you are looking to do Python-based programming on a microcontroller, that means you will need a more modern one and usually a slightly more expensive one. So if you have a look at the projects that we have here, the microcontrollers that are in these projects, if we wanted to upgrade them to something that could be Python, it would be about like $3 to $5 more expensive for the project just to gain that capability. Which maybe if you're particularly cost constrained, you don't go in that direction. But if you like Python as a language, which it has its own benefits, and as far as like programming languages to learn early on and like your text-based coding career goes, like Python is easier to learn.
Yep.
So
it's worth saying that the microbit is the de facto England. The BBC actually designed and I think distributes the microbit. Like it's designed for kids to learn with in England, period, the end, full stop.
Is it free? Because I know my education, you know, I could figure that one.
That's a really good question. I don't know. And it might be different in England versus here. They cost like $35 a pop here. Yeah, just keep going.
Yeah. And then Adafruit has their own foothold in the Python-based microcontroller programming niche, which they call Circuit Python. It is a similar story to the way that the Arduino IDE works. So you get an app in which you write some Python code, you plug in your microcontroller, you push a button, the code goes over, and then it does things. They have, in their Adafruity way, they have endless tutorials about this. And these days, when they're writing a tutorial for a specific peripheral, like maybe for a temperature sensor, in that tutorial, they will have one page that is how to make this programming work with Arduino IDE, and there's going to be one for how to make it work with the Circuit Python. Yes.
And then we got one more to show you,
yes,
but mostly just so you don't mix it up with Circuit Python. Yeah, I have to check every time. But Circuit Python is probably the one you want to be playing with unless you already know what you're doing. And then MicroPython is what Circuit Python was based on.
Yeah. So Circuit Python is Adafruit's version that has tutorials and instructions, and they will show you parts that work with it and all of that stuff. Whereas MicroPython is sort of the underpinnings and the scaffolding that is based on, but its tutorials are useless. And figuring out what it's compatible with is also a nightmare. So it's here to tell you not to go there unless you are very advanced.
Right. Yeah. Don't. If you see the red snake, no. If you see the purple snake, yes.
The purple and the pink are a little friendlier.
And it's smiling.
Yeah,
look at it smiling.
It's got little eyelashes. He's pretty cute too.
He's cute though, but
right.
You know, the eyelashes. That's what.
So start with the lady snake.
Yeah. Yeah.
Unfortunate to like gender.
No, it's whatever.
Okay. So that's a whirlwind tour of the endless rabbit hole that microcontroller programming is. But the punchline for you is all of the projects that we have for foundations, they're all in Tinkercad, and they have block-based code associated with them that you can look at and you can see what the thing is supposed to do. And then Tinkercad will give you that text. And then what we're going to do is, as people are making their way through their projects, we're going to show you how to get that text-based code onto your microcontroller. And it's usually going to involve either installing the Arduino app on your own computer or using one of our computers to do it. But there is, the other punchline here is that you can, in fact, that was there for a reason.
Oh, okay.
That node takes up all of this space.
Yeah, no, we'll move it around when we need to.
Yeah.
But in here, this is the
blocks and text.
That's right. I clicked on the wrong thing.
Yep.
This is the big idea with what's going on.
Yeah.
That's our code.
That is literally the entire logic of the motor that it needs to do to like switch direction and turn on and off as needed is like 20 lines of code though. Yeah.
How did we get that?
you go to Tinkercad, link for whatever project you want to look at, and all of them got posted in Foundation Slack at some point.
They did.
They were, they were like.
Yeah.
Yep.
I don't know.
And the short version is the pin on the top of the box, the switch on the top of the box is tied to pin 9, and the switch that's inside the box is pin 8. And basically, the control is based on the state of those 2 switches.
And you'll be here on Sunday to help us.
And
And
we'll
also
be
today.
and today.
Also, because Corey handheld me through doing this on Sunday, something that you'll encounter once you start putting it together, but that I 100% never would have figured out from just looking at this on my own, is that we're not using.
Sorry.
Stop it, sorry.
Stop touching.
Go away.
All
Go farther away.
Okay. All right.
Keep going.
Oh boy.
There.
Oh,
Sensitive.
It is.
You know this button?
Yeah. No.
Is that we're not using an Arduino.
Yeah.
We're using this little black.
Metro Mini.
And so these are not
There are no wires.
wires. These are indicators of where the pins insert into. Because this little, like, pretend this is just that little black box, and then it's like sets into the board.
no, this,
Yeah,
this and this.
And the wires are these pins. Yeah. So
Yeah.
Be here on Sunday.
Yeah, we're gonna help you
it
do
was-
it.
I was here last Sunday and I'm so glad.
Yeah, it's a good one to come in for.
Yeah,
It's trickier than a table saw.
yes, yes.
Related.
Yeah.
It's dangerous.
Yeah.
Honestly, with Corey sitting next to us, I felt like it was very, and I'm sure it would have been the same if you were here, just like having a human there to just like, okay, now do these things.
Yeah.
And I will say, like, I opened this whole module by saying that the only skill that you need to know is how to find a good tutorial and how to follow it. This is not an example of a very good tutorial. Like, tutorials are better than the tutorials we have here.
Yeah.
So do not hold yourselves if you got confused anywhere along the way in these directions.
I get confused all the time. I don't mind anymore.
Yeah. Okay. So that ends my story for the evening.
No, I think that's it on the new stuff, because that's already a dramatic amount of new stuff. So we'll just, I think the goal would be 1, to do the show and tell and hear people have been up to, and then 2, to hang out and point at things and try and help and see if we can upload code to anything, because that's something that we can totally do. I've got a little cord here and I've got the code. I pulled this up so that I could download the code so we could upload it to your board. And then all you would need is power to know if it worked when you finally get to the state of running it. So that's where we're at.